All right, in this video, we are doing a quick recap of some of the convergence tests that we've talked about. We're not doing anything new in this video, so if you're feeling great about convergence tests, feel free to skip this one. That said, I think this is a useful thing just to keep all of these different tests straight. Okay, so starting off, the main question that we're asking is, how do we tell if a series converges? And again, just to reiterate, when we're talking about a sequence, which is just an infinite list of numbers, if we want to know if that sequence converges, we just ask, all right, are these values approaching some set value? For example, 0.9, 0.99, 0.999, that sequence appears to be converging to 1. So since that's a finite number, we're going to say that it converges. For series, however, we're taking this infinite list of numbers and adding them up and asking if this infinitely long sum is some finite number. And this is actually sort of a deeper question than it is with the sequences. In fact, we really need the sequence to converge. We need to converge to a finite number, and we need to converge something to actually just 0. So that actually brings us sort of to our first test, which we haven't yet called it the divergence test. I put it in quotes because we haven't used that language before. But if you're reading about this elsewhere, you'll often see this referred to as the divergence test. And this test is really just a sanity check. It's saying, are we talking about a series that even could possibly converge? For example, if we're asking about the series 1 plus 2 plus 3 plus 4 plus 5 plus 6, etc., well, the sequence doesn't even converge, so there's no way that that sum is going to be something finite. Right? That's the divergence test. It's using this logic just to weed out the completely ridiculous series that can't possibly converge because the sequences don't even converge. So I would say that there aren't any requirements to use this test, and the conclusions that we can draw. The only conclusion you can possibly draw from this is that it diverges. If nothing seems wrong with it, then we can't really use this test. It doesn't really tell us anything. We cannot possibly do this so just because the sequence the sequence that represents the series might approach 0, that doesn't necessarily mean that the series converges as well. So we can't make a conclusion saying that the series converges. Okay, so the integral test. This is a test we can use if our sequence is positive and decreasing. And so if we're in a situation like this, something like 1 over n or 1 over n squared are two examples we've seen. If we're in a situation like this, then rather than talking about this as a series, we can think of it as an integral. We can translate 1 over n to 1 over x and integrate that and ask, does this integral converge? And if that integral converges, then we conclude that the series converges. If the integral diverges, we conclude that the series diverge. So we can draw either possible conclusions. The comparison test, the idea is that we have some other series that maybe is written in a similar way that we understand through some other means. If the series that we're actually asking about differs in some simple way, as in maybe it's, for the most part, just less than what the previous series was, then we can compare the two and make a conclusion that it converges or diverges, depending on if it's less than or greater than. So the requirements for this is really just another series that we understand in some way. The limit comparison test. Is also requires that we have some other series. And again, we're going to be comparing the two in a slightly different way, rather than saying that, all right, for the most part, one is always bigger than the other. What we're going to say is, well, what we really care about is what happens at the end. If we take the limit as n goes to infinity of the ratio of the two, that ratio, the number that we get, is going to tell us something. If that number is 1, then that means that our two series are linked, as in if one converges, the other converges. If one diverges, the other diverges. So here we can draw either conclusion. For the ratio test, we're only working with one series. We're not comparing it to anything else. But the way it works is that we're going to take the limit as n goes to infinity of an plus 1 over an. In other words, we're saying, oh, in absolute values. In other words, we're saying, all right, what is sort of the end behavior for this? Like the next term, does that increase or decrease? Or if it decreases, how quickly does it decrease? And with this thing, depending on what number we get here, which we often call L, we might conclude that it converges. We might conclude that it converges. We might conclude that it diverges, or we might conclude that it's inconclusive. That if the number we get out here is 1, we don't actually really tell anything. The last test is the alternating series test. The main condition to be able to use this is that our series is alternating. We also need the sequence to be positive and decreasing. And sort of similar to some other ones, and if we have a situation that, if we have a series that meets these conditions, that's alternating, it's always positive, it's always decreasing, it automatically converges. Like, no matter what the rest of it's doing, we get a convergence statement for free. Okay, if you were a little iffy on any of that, I highly recommend that you go back and watch the corresponding video describing this in more detail. If you're still iffy on it, then that's a great thing to talk about in your section. If you otherwise, don't worry about discussing this particular video in your discussion groups. This is mostly just as a recap for your purposes, for your just to keep things straight.